One very important example of how to apply the concepts of interactions within subsystems in a complex system is provided by how epidemic spreading happens. Okay? Epidemics is important for many reasons. One quite obvious is that the spread of pathogens, that could be viruses or bacteria, in human populations or in general in natural populations leads to profound or can lead to profound changes. It also is connected to our long evolutionary history connecting us with these pathogens, okay? And also for humans, the impact they had on civilization. And if we look at the historical record of how big pandemics changed human populations, the result is quite frightening. Viruses and bacteria have killed millions of people over the last millennia. And the more the population is growing, the more it's likely that actually new viruses emerge, what we call emergent viruses. Mathematical models are not only here useful descriptions, they are actually absolutely crucial to actually understand the nature of epidemic spreading. And at some point we'll also learn that these models can be applied to actually do other kind of models, for example, of how activity spreads in the brain. So in this lecture we will introduce an extremely simple model of epidemic spreading that nevertheless has been extremely useful to understand in particular the presence of thresholds that separate whether or not epidemic spreading happens. In general, epidemiology is a very mature science, very well established, and that has been key, for example, for managing or trying to manage the COVID-19 pandemic event. And we can always distinguish, as is going to happen in anything we study here, a multitude of levels of complexity. And I'll try to locate you where are we going to be working today. There's a very high scale level, the planetary scale, and now I'm talking about humans. Well, you have to take into account things like airports, urban centers, and in general, the networks that make human mobility a reality that we know today, okay? The global reality that we know today, that in particular makes possible something that was impossible 200 years ago, which is that a given pathogen can propagate at the planetary scale, right? In the times where transportation was essentially geographic, you have to move in space, so to neighborhoods, that's not going to happen anymore. So that makes a difference in many ways. There's more scales than the ones I'm presenting here, but if you look at a local scale in these propagation networks, you can also look at the networks that are more close to us, the social networks, okay? Social interaction networks. All right, where these can be dynamical, but also have some static properties, right? Depending what level of network you define, right? The close neighborhood in terms of friends and family, or just the networks of acquaintances of people that you met over the day, etc., etc. Nevertheless, here the nodes, okay, of this network involve pairwise interactions. Again, that's what we want, right? So that could be a human, okay, and that could be another human, right? And here we're talking about connecting them by some kind of interaction, right? And that's the level we are going to explore. In other lectures, we'll see lower levels of description, and when you go into the actual dynamics of how the pathogen interacts with your organism and your cells, that means that you need to go at the level of how viruses are able to infect cells, right? and what kind of strategies the virus uses to do the infection, or maybe just remain in your cells for a very long time, as it happens with the HIV virus. Okay? Again, many levels of complexity, but the pairwise interaction is our first layer of definition. And what we're going to do is assume the following. Suppose we have a pathogen, a virus, or a bacterium, suppose a virus, for example, that is able to propagate between two kinds of individuals, right? And this defines, it's called the SIS model. Extremely simple model, as you will see. Imagine you have individuals that are healthy, right? In the literature, this is what we call the susceptible individuals. Those individuals then can be infected, right? And the second group, individuals that are infected and can interact with the first, and we'll call this population as I. Again, I'm going to use, right, this will be, I'm going to use S and I as population or as identifier of the kind of individual, okay, for simplicity. All right, what kind of things we know about that? Or to rephrase it, what kind of things are reasonably to assume for a minimal model? Well, the following assumptions define the SIS model. The first is, if I'm infected, at some point I can recover from infection, right? I can get healthy again. In other words, an infected individual in a spontaneous way, right, can go back to the healthy state. Let me call alpha how fast this process happens, how easy it is to recover, okay? So this weights this quantity. It doesn't depend on anything. You're sick, you go home, you rest there, and you recover, right? The second mechanism is more sophisticated, it's more important, and includes a non-linearity. To get sick, right, I cannot get spontaneously sick. I cannot just be healthy and then be sick. I need to get with someone who is actually infected. So, a pairwise interaction. I need susceptible and infected to get together, right, somehow, to have two infected people, okay? So the susceptible has made the transition. Let's say this is mu, right? The probability or the rate of infections, assuming that two individuals get together, right? This, of course, captures a lot of things. Can capture that you need to get into contact, or you just need to be in a bus where somebody snorts and spreads the virus, right? Okay, that's the assumptions. What is missing here? Well, this is an extremely simple model, and we immediately have in mind the idea that in many cases what you actually have is that when you get infected and you recover, you might not get infected again because your body has created the immune defenses that actually prevents that to happen again, right? That is what is called the SIR model. You have recovered individuals that are not going to go back immediately into the infected state. They are protected. We are not going to assume that. And the more complex is the description, the more compartments you need to add. For example, if you want to make a model of Ebola, then you have to include not only infected and susceptible and those that got infected at some point and are immunized, you need to consider also corpses, right? Because for a long time, what happened is that people went to the funerals and touched the dead bodies, which were infecting people. So it's a compartment that you have to take into account. So if we limit ourselves into that, we'll see that several really interesting things happen. So how can I make a model of that, right? Well, I need a model for infected and for susceptible, right? Another assumption I'm going to make is that the total population is constant. So the number of infected plus susceptible is not going to change over time. Nobody dies here. Nobody immigrates. So it remains constant. Okay? So I'm going to make another assumption. To make the model simpler, right, I want to normalize it. You have a population, so you want the total population is the sum of I plus S. I'm assuming this is constant, okay? And I want to consider normalized populations to make things just simpler, all right? So if I redefine I as the relative fraction and S as the relative fraction, okay? So I don't want to use other notation. In that case, S plus I is equals 1, right? Just a relative fraction, okay? Very good. So I'm going to use this for writing down the model. One very simple process is decay, okay? If I'm infected, okay, I am back into the susceptible state with a rate, and since I'm leaving infected individuals that get susceptible, this is going to be minus alpha I, right? And of course, where do these individuals go? They go into the other compartment. Each time that one infected recovers, goes here, okay? Now the other part, now we know how to deal with that because it's an interaction. So every time a susceptible and an infected get together with some rate, mu, a new infected is created. So this grows every time this pair gets together. It's a product, okay, as we know. And of course, every time this happens, someone who was healthy moves here, okay? So essentially we have a flow in two directions. In a way is I lose someone here, that goes here, I lose someone here, that goes here. Overall, right? Despite this seems a two-dimensional system, it is not. Because if you make the sum of both, right? And you can check that for any model you formulate, this is 0, which has to be. The total population has to be 0, all right? Okay, knowing that, we can solve the problem. We can solve the dynamics of the system easily, right? Because take, for example, infected. I take infected because one important thing we want is to say how many infected people I will observe in the population, all right? And I can simplify this model. And now I'll take advantage of what we have learned about stability analysis, okay? It will be minus alpha y, okay, plus mu infected, but S is just 1 minus I, all right? Because the sum is 1. So, as it happened with other problems we have explored, this is not a two-dimensional dynamical system. Because of conservation, this is the equation that describes the propagation dynamics of an epidemic event under the SIS approximation, all right? So, again, we could solve this model, right? Let me point out, remember the importance of finding equivalences between models referring to different phenomena, right? If I write down this slightly differently, I can write this. I want to put this part here inside the parentheses, right? It would be something like this. And if you look at that, you actually see something that we have already seen. This is a logistic model, okay? Mathematically, it's a logistic model, except that there's something interesting here, right? This would be for a logistic model with k equals 1, right? For k equals 1, will be nothing in the denominator. And we have here something that says that you're not going to reach 1, right? We're not going to have everyone infected. You always will have a slower value that depends on what you have here, okay? All right, well, let's say take the model. We can take it this way because we have factorized the two parts, right? We don't want to do the integral of this or anything. Let's do the fixed point analysis, right? We want to know what are the stable or unstable fixed points, okay? I'm not going to go into all the details. That's something for you as an exercise, okay? But look, how do we find the fixed point? We just need to take this function here equal to 0, right? That's the condition for stability, or this one here, more easy, right? Either population is 0, no infection, so that means the infection or the pandemic is over. There's no infection, right? Or this here is 0, which automatically gives us another fixed point. In many cases, this is called the trivial fixed point because it's kind of there's nothing there in reality, but it's very useful to actually manage to calculate things. And this is the non-trivial fixed point. Here, if that quantity here is less than 1, we have pandemic or we have epidemic spreading. We have a population of infected individuals, right? Okay, so how do I know if this is stable or not stable? Well, this is an interesting situation because now stability is not going to be black or white. It's going to depend on the parameters, depending on how efficient is the virus for infection, how strong is the recovery process, I will have or not propagation, okay? Very good. If I do the stability analysis, right, let me remind you how it works. What we need to do is to calculate these, right? I use the mu here, I have a mu and a half alpha, but just put one parameter that's going to be particularly important for us. And this is just the derivative of my function that now depends on I, so that will be my function. Okay? Let me pick here this. I do the derivative, just need to make these, so do we mu, I will have 1 minus alpha over mu on the one hand, minus 2i on the other, if I'm not wrong. Okay. And now I need to put inside, remember, what we need to do is, this is the derivative. Inside, I use the different fixed point values and see what's the conditions under which is positive or negative. Let's take it the 0, right? That means what I want to find out is under what conditions I will see that my pandemic, my epidemic event is go to extinction. It's not, it cannot grow, it goes to extinction. So I just need to put here 0, all right? Means that what remains is this, right? And so actually if I rewrite that, I get into this condition, okay? Very good. We haven't found that in the previous lectures. In the previous lectures we saw one thing is stable or unstable. Now it depends. It depends on the parameters. So this will be stable, and so we will see that the virus is unable to replicate and the pandemic is over, right? If, and only if, right? If this is negative, because negative is the condition for stability. Mu, if that happens, no propagation is possible, which means that this is the condition for the pandemic to get extinct. Look, this seems to be quite reasonable. Biologically, what I'm saying is, if the propagation, again, this parameter includes how efficient is the virus to go from one individual to another in an infection event. If propagation is less efficient than recovery, so how fast infected individuals go into the healthy state, if that happens, the epidemic is not going to function, which actually is a very interesting first observation. It means that for epidemics to spread under these conditions, you need to overcome a threshold. And as we will see, this is a crucial idea in terms of vaccination. If you want to vaccinate the population, you need to actually be able to manage that threshold, right? And that's a very, very general lesson, okay? Well, you could say, okay, now I'm going to do the same for the other fixed point, right? For this. But in fact, that's a very general rule that we're going to apply. When you have two different fixed points, right, two alternative fixed points, the stability is exchanged, right? Often it happens because actually this fixed point doesn't exist under these conditions. You can check out, right? It would be negative. Negative population doesn't mean anything, okay? So if you take the second fixed point, it's easy to see, right? You do it, okay? You just will find out that this gives exactly the opposite, the contrary condition, right? Which means that the pandemic, if you want, or the epidemic spreading state is stable if and only if the contrary condition happens, meaning that the efficiency of the pathogen to propagate is higher than the recovery rate of individuals, right? Very good. Actually, sometimes we can rewrite this in a different kind of formalism, usually more sophisticated than this. But look, this condition here, right, can be also written in another way, right? If I define a parameter R0, okay, if you look at this here, for example, you could say if mu over alpha is less than 1, just dividing in both sides. Here will be mu over alpha larger than 1, right? With a single parameter that captures both recovery and infection, right? I find out one way of actually saying under what conditions propagation happens or not. And the condition of propagation is whether or not I go beyond 1 or below 1, right? In epidemiology, in particular when we do mathematical modeling, this defines the condition when actually I'm going to be able to at least propagate the infection to one individual. I'm saying that very, very mildly because we'll go back to that in more detail, but essentially is the condition under which, to the least, I can maintain the number of infected individuals, right? Okay, now the thing is, these ideas, stability analysis, the presence of a threshold, can be captured by a single diagram that provides a lot of ideas about complexity in general, and in particular the complexity of epidemic spreading. This is what we call the bifurcation diagram. We have seen that the SIS model gives two potential states, which are the two possibilities for an epidemic in terms of the number of individuals or the fraction of the population that can be infected at a given step. And we just found out that if you look at the stability, epidemic spreading meaning that the second state is stable, right? So that this is positive, is stable if R0, which we define as mu over alpha, is positive, is larger than 1. Okay? And on the contrary, there's another state, which is the epidemic is unable to succeed, goes to 0, right? When the opposite condition happens, right? This is a crucial parameter that is absolutely central in epidemiology. Even if you are not in this framework of the SIS model, you can, for any model you can describe, either mathematical or computational, you can find out, and you have to find out R0. Because if you want to know if any method of containment is working, you need to put the population below this value, right? So containment, ideally, containment means that you put the virus under control and make it to get extinct. Containment happens if this is less than 0, right? During the COVID pandemic, this has become a really central object of discussion, and it's a kind of the essential thing you have to control to see if things are going well or not. Incidentally, in Contagion, the only movie about epidemics that kind of makes sense, so it's not about zombies running like crazy after people to eat them. In Contagion, Kate Winslet, the famous actress, actually describes the idea of R0, right? So it's pretty general even for the movies. So all this brings us into a very important mathematical object that we'll explore and that captures a lot of the complexity in nonlinear systems, which is the bifurcation diagram. The bifurcation diagram is, as the name says, is a single diagram that captures almost everything that happens in one of these models, right? So whether things are stable or not, whether you have transitions between different states, virtually everything, right? How do I build it? Well, what I really want to know in the end is whether or not I'm going to observe a population that is infected or not, how much of the population, what is the amount of people infected, okay? And what are these threshold points located? I want all this. So let's do it. Let's write down this diagram where I'm going to use as an x-axis now a parameter. So it's not time or a given variable in the system, but a parameter, right? A very different kind of diagram of what we've seen so far. And in the y-axis, I'm going to put the equilibrium states, so how many infected people I'm going to observe if I wait, right? And we'll define the size of the epidemic event. What things do we know? Let's put here 0 for zero propagation of the pathogen. This is 0 for the infected individuals, and we know that there's a maximum amount of infected individuals, which is the maximum population size, that remember that we normalized, right? For simplicity, we assume that S and Y are relative populations, okay? And that's the maximum. So another thing we know, we just knew from stability analysis, is that somewhere, right, there's a value of mu that defines actually the threshold of propagation, right? If mu is larger than this value, I propagate. If mu is smaller than the value, I don't propagate, right? So when mu, and I indicate that as critical, right? When mu has a critical value equals alpha, I separate two domains, right? In one size, here, that defines epidemic dies out. It cannot propagate, right? Whereas in this part here, when I'm in this domain, I have epidemic spreading, okay? Well, in physics, we tend to talk about these kind of separated states or phases as phases, right? Like in phases like water and steam, etc. We say this is a phase where no epidemic spreading happens. This is epidemic spreading phase. All right, so how can I put all other things here? Well, see, in this part here, what's going to happen if I'm below this threshold? Well, what I'm going to see is that because I'm unable to counterbalance the recovery of individuals, right? If I take a given value of mu, right, my population is going to go down, right? In the effect, they're going to go down to 0, which is the equilibrium state. No epidemics. If I take another value of mu, I'm going to go to another equilibrium state, again 0, right? And the same happens for anything here. The fastest here, slower here, right? But essentially what I'm saying is any value I can take here of mu leads to an equilibrium state that is stable. And we indicate that by connecting all of them, right, with a single line, right? This is stable, right? Any condition here goes to 0. Okay? All right. Mathematically, I star equals 0 exists here, right? In this domain here, if I am in the state 0, there's no epidemic spreading, of course, because if no one is infected, no one will spread anything. So I indicate the presence of this point. Let me put this a little bit up this here. We've got this continuous line, saying this continuous line for me will mean unstable, whereas this will be stable, right? In this way, in a systematic way, forget about this here. This is not anything to do with that. This is a limit. This means that in this phase, this is stable, this is unstable, meaning that even if I add a small amount of infected people, it will propagate, right? It will propagate, so I go far from that. This is unstable, all right? I propagate up. Where? Well, if I'm here, right, what is the shape of the equilibrium state? Do I know it? Yes. This is the expression that we just found out for this. And if you look at that, you can see that for a given alpha, whatever the value, right, if I keep mu increasing, this quantity here, right, will go rapidly shrinking to 0. Right? If I plot this, which is a function of mu, what I'm going to see is this. All right? This here is the amount of people infected, right, for a given alpha, well, so it is a very general thing, when I cross this threshold here. Clearly, below this threshold, this doesn't exist. It would be negative. But essentially what I'm saying is, and it's continuous line, right? Anything I have here, small perturbation, I add an infectious particle here, and the system rapidly moves in this direction. And for a given mu, any mu I want to take, this is the amount of people that is infected, the fraction of people in the population that is infected. This is what we call, this is what we call a bifurcation diagram. A bifurcation for us, and we'll classify the different types of bifurcation at some point, means a point, in physics we call this a phase transition, a point where a qualitative change happens, right, between two phases, between two kinds of dynamical states and structural states. In physics, this is very clear, right? Could be in different contexts where phase transitions happen. In this case, means that there's clearly one phase where I observe a die out, no epidemics, from a phase where I have propagation of epidemics. In terms of complexity, this is a very, very important message, because one could think that that's what our intuition will say, right? One could think, well, if some virus is able to infect individuals, the more infectious it is, the more people will be infected. So my intuition will say, maybe the number of infected individuals will be something like this, right? The more infection, the more. But it's not true. It's a threshold that separates very sharply what can happen from what cannot happen, right? We will further explore these ideas. This is central to many problems in complex systems that consider whether or not information propagates in a given network, for example. And as an exercise for you, consider the following. When you vaccinate people, what are you doing in terms of the dynamical state of the system? When you vaccinate, what you do is, in the model we just described, let's make a diagram that puts everything together, right? Susceptibles can get infected, right? Provided that there's an interaction. Infected can be susceptible, right, in a spontaneous way. What happens to this diagram, and that's a very important point here, if I vaccinate people? If so, vaccination means that you take on one part of the population and subtract that from the potential population that the virus can infect, right? Essentially what it means, as a hint, that in this diagram, where I put everyone here or here, right? There's a third compartment, but it's a constant. It's not a variable. It's a fixed number of individuals. Let's call it R. That could be some number between 0 and 1 that gets outside of my dynamical system. You can show, and that's the exercise I propose, that when you add this term here, you put out from circulation of a fraction of the population, what you do, actually, is to move, to move the diagram in this way. So you push the potential of the virus for infection in this direction, the threshold, excuse me. You put the threshold here. What means is, and that's the final message here, that if I'm a pathogen, okay, and I'm in one domain where I'm able to infect part of the population, right? I have been evolving and ready for infecting that particular population. But if you push this boundary, the threshold here, then somehow I have to reinvent myself. I need to now be more effective to actually have populations in this domain. But of course, evolving so quickly is probably impossible to happen. And that's why vaccines can work, even if you vaccinate one fraction of the population. You put the threshold somewhere else, and the epidemic goes down, right? That's the big message that you have to take from this idea. And very particularly the idea that one of the crucial components of complexity is that, and that applies for bioengineering, for diseases, for many conceptual ideas, is that thresholds and phases exist. And we have to understand the reality of biocomplexity by taking them into account.